whether or not it's due to freezing and thawing in the winter or heating in the summer. Finally, the last grain that's holding the material up breaks up into pieces, and then the block falls. It's a very slow process, but it occurs in sporadic events. You might call this catastrophic events.
This kind of differential erosion accounts for the look of the terraced layers of the canyon walls over the last 1.5 million years. The full story of the Grand Canyon's creation is much more dramatic and is still being debated. Over millions of years, the surface of the land, which is now the Grand Canyon, rose and fell with tectonic activity. At times, the area was flooded, creating a marine environment where debris settled to the floor. This debris was then compacted into layers of sedimentary rock. As the Colorado River formed, it began to cut into the sedimentary rock. It has long been thought that the river carved the canyon's present course between 6 million and 1 million years ago. However, new studies suggest it may have begun as long as 17 million years ago. Given the strength of the bedrock and the need to minimize impact, the engineering team studies various options for Skywalk's foundation.
I got thinking it would be very difficult to attach it to the cliff, so I made the decision to bring it above the cliff and then lock it down to the top of the cliff and place the visitor center on top.
To lock Skywalk down to the top of the cliff, the team decides to build the foundation directly into the rock with caissons and micropiles. The 4 caissons are reinforced concrete columns. Micropiles are an engineered system of threaded steel bars that go inside the caissons, adding strength. Each micropile measures 6.5 centimeters in diameter and extends 14 meters down into the rock. This method of reinforcing a foundation is called post-tensioning. With the plan in place and work about to begin, the Wallapai blessed the construction site on October 1st, 2004. A month later, the tedious work of drilling begins, using diamond-tipped drill bits and compressed air hammers.
Very difficult. Put it this way, I mean, they were breaking tips on the bit like every 5 to 10 minutes, they were breaking a bit. So that tells you how hard this rock was, and the material that we were trying to core through was extremely hard. Some of the hardest material that I've ever encountered.
As drilling proceeds, an unexpected and potentially devastating problem rises. The hole being drilled for one of the micropiles appears to be heading toward an intersection of 2 geologic cracks in the bedrock.
It was fairly evident that the chances of intersecting one of these joints by the drilling operation was fairly high. And as it turned out, they did intercept one of the vertical fractures, and some of the compressed air used in the drilling escaped along the fracture, which indicated that it might be open a little bit.
If the fracture opens too much, the entire project is in jeopardy. The builders might have to start over at a new location.
I thought it prudent to go over the cliff in a cage and take some measurements and to look at the joint system below the top of the cliff.
6 meters below the rim, John Peck finds the open fracture on the rock face. It reaches 4 meters into the canyon wall, just 1 meter from the hole being drilled for the micropile.
That caught everybody's attention.
The team decides to implement a rock bolting system inside the caisson to stabilize and reinforce the fracture. Using a grid of horizontal and vertical steel bars, they literally knit the rock together across its fracture pattern. This alleviates the pressure on the crack. The solution works. the crisis is averted and drilling continues for the micropiles. Once in place, both the micropiles and the rock bolts are encased in concrete, along with 2 steel columns over each caisson. These will become the attachment points for the Skywalk structural frame.
So this is the foundation for 2 of the 8 columns for the Skywalk, and basically it's a concrete cap that was poured on top of the micropiles and caissons below. And we also embedded this 2'8" square steel columns in the concrete to actually support the box beam Skywalk itself.
A year and a half after drilling began at the location, Skywalk contractors finished pouring the concrete foundation. David Jin and his family are there to celebrate the moment and mark the spot. The foundation is tested to assess its ability to support the projected load, and it exceeds all expectations, measuring strong enough to support over 32 million kilograms, or the equivalent of 71 fully loaded 747s.
We actually went overboard, I think, in some areas. So we did a lot of extra things according to the geologist's recommendations and the structural engineer's recommendations to make sure that it all went well, because this was never done before, and this type of a construction project was never done before.
For the Wallapai, building Skywalk is an important step to the future. But it's equally important that future visitors respect their past, their customs, and the land they call home.
Wallapai people have lived in this part of the world since the beginning of time. That's our belief.
It was natural, quiet, peaceful. They say the wind tells you things, and if you really listen, it does.
The Wallapai are traditionally nomadic, migrating over lands from the Colorado River southeast to Wickiup, Arizona, and from the current site of the Hoover Dam east to Flagstaff, over 24,000 square kilometers. In the 19th century, the population of the tribe was decimated by war and disease. Their land was occupied by white settlers, forcing the Wallapai to live on a reservation. Established in 1883, it covers just under 4,000 square kilometers, reaching the edge of the South Rim. Since the 1950s, the Wallapai have considered various business interests, with the primary focus on river rafting and West Rim tourism.
We don't have the other industry that other Indian tribes enjoy simply because of their location. But in a way, we're taking advantage of this location, and there's a delicate balance between nature and development for the Wallapai people.
In developing Skywalk, the Wallapai are counting on the delicate balance of a horseshoe-shaped bridge hanging over a huge cliff. And the key to making this happen lies in the beams that support it. Skywalk's major support beams are called box beams. These are giant, curved, hollow steel beams specially designed to handle huge loads of weight and stress. These box beams are 2 meters tall and large enough to walk inside.
These beams are 32 inches wide, 72 inches deep. They're made out of 2-inch thick steel plate, 50,000 psi. So it's a very strong steel plate, very large box beam section. Right here we have one of the cross beams, but this cross beam is to help lock the 2 beams together.
Another function of the box beam is to absorb vibration and avoid galloping in windy conditions. Galloping is a wind-induced movement on a support beam, which causes amplified oscillations and instability. In a worst-case scenario, galloping can cause catastrophic structural failure. such as the collapse of the Tacoma Narrows Bridge in 1940. The galloping was caused by modest 65-kilometer winds. To prevent any galloping at Skywalk, where winds are significantly higher, the box beams are made with 5-centimeter thick steel plates. Their hollow design is engineered to flex in the wind and absorb vibration. The beams are custom fabricated in Utah in 12-meter sections and then trucked to the Grand Canyon. Shipping the box beams is a big endeavor. It takes months for all the sections to arrive at the location.
Once they were here, it's a matter of just turning the crew loose and going to work and putting them together.
For safety, the Skywalk is assembled over land. It will be rolled out over the cliff later. First, permanent caps are attached to the 8 concrete columns. These will help anchor the Skywalk. Next, the crew builds a network of temporary sawhorses to support the box beams as they are positioned for welding. Finally, the box beams are lowered into position using a large construction crane.
Really took a lot of precision in layout to put all the parts and pieces together. A curved structure that's 2 inches thick is not an easy thing to put together within 1/8 of an inch of accuracy.
After the sections are precisely aligned, welding begins on the 500,000 kilogram structure.
It took quite a bit of welding, quite a bit of visual and x-ray inspections of the welds themselves to make sure that they adhered. A lot of time, a lot of months in welding that entire structure together.
It takes a month to weld the horseshoe-shaped frame together. With the structure complete, the reality of a cantilevered bridge jutting out over a 1,200-meter drop weighs heavily with Bill Karen.
One of the things I've thought about all through this project is I want people as they walk the bridge to feel safe and comfortable despite the fact they're walking on glass and looking thousands of feet down the face of a cliff.
The combination of wind and the weight of random foot traffic on the Skywalk will cause vibrations on the structure, potentially frightening to visitors. This problem has to be solved. The answer is an engineering device called a tuned mass damper. Like shock absorbers, tuned mass dampers counteract vibrations by applying equal pressure and force in the opposite direction. Here, a weight mounted on springs counteracts wind and weight vibration, stabilizing the structure and dissipating energy as heat generated by the friction of the movement. 3 TNDs, each weighing 1.6 tons, are specifically calibrated to meet the wind and weight requirements of the location.